Hello everyone, good afternoon. I hope you all are doing well today. And thank you for joining us for this session of our fall 2024 seminar series organized by graduate student community. It's great to see you all here. Before we begin, I would like to take a minute to acknowledge our wonderful GSC leadership team. They have been worked very hard to organize and promote this series. Our team includes lead by Rachel and Roshan. And also we have our support team with the graduate students from multiple schools of Gallagher Engineering College. Our team is mentored by Dr. Khalid Nasri. So to be connected with GSC, and we usually meet on Thursdays at 2 p.m. At the Dave and Susan Burke team room. From this semester, we have started meeting in person. So if any of you are interested to join our team, you can email Rachel or Lucian, or you can contact Dr. Mystery as well to join our team and join our meetings. So, and be connected with us. You can follow us with Engage. So you can scan the QR code and join our Engage page as well to be connected and to be well informed about our events. And after that, you can join our LinkedIn group as well. So we are also active in LinkedIn, so that if you can want to post anything in our LinkedIn group, you can do that. And we have also a Facebook page. Please do follow us over there by scanning the QR code, or even you can search the name of our Facebook page to get it. Most of those sessions are usually recorded by Dr. Mystery, and we usually posted that in our YouTube channel. You can go ahead and look up our past sessions, and also if you miss any part of our today's session, you can also check out that over there. For the leadership team and all the members of our GSC community, we have a dedicated workspace or room to chat. It's in the Dave and student work team room. If you need the access of that room, please contact Rachel or Ocean, or you can email the Park Mystery to get the access of that. So if you want to get some bread, take some bread, and just go there to chat with your friend, you can go there. We have a lot of communities over there. And please don't forget to fill up this form for attendance. And now into today's seminar topic, digital manufacturing and the journey to democratization. We had the privilege to have Dr. Sashiva Kumarani, the director of the School of Industrial and Systems Engineering, government, here with us today. He has definitely a lot of knowledge and experience in this field, and I'm sure we are all eager to hear from him. With that, I would like to hand the stage over to Professor Raman. Let's give him a warm welcome. Thank you, Dr. Raman.
Hi, how do I share my video?
You just go to share in Zoom and share your screen.
I can't see the share link. That's the problem. I joined on your just 1 second. I'm trying to figure out how.
At the bottom, you will see a green thing with an arrow saying share.
No, okay. Now I see it. Okay, good. Thank you. I was just kind of wondering why it wasn't showing up. Okay, I don't know where did it come now. Okay, this is not it. Oh, I think you shared my desktop. Okay. Okay, so just would like to kind of tell you that I wanted to go through my journey, and I know some of you who heard the more abbreviated version of this sometime in fall. I did talk to the SRL students, one of the morning meetings. So this is not too very wildly different, because this is the area I am working on right now. So basically, I've been here at the University of Oklahoma for 36 years. And so I think I started with an infographic here, which is basically, I wanted to try and move a lot of these things that are keep coming in here. Okay. Oops. Okay. So, okay, that's good. Okay, so I basically, I'm a mechanical engineer by training initially. And what ended up happening was that somewhere there, I kind of saw the light and moved into industrial engineering when I was doing my PhD. I joined my PhD mainly to work on a continuation of my master's, which was basically in applying control systems and sensing to toolware modeling or toolware monitoring. So basically, in machining processes, the cutting tools wear off. And so the whole process was that we used to use vibration monitors and cutting forces to kind of monitor the signature analysis. We did signature analysis to try and create some kind of a model that will detect tool wear without having to stop the machine. So online monitoring of tool wear, which kind of evolved into, it was not very physics based at the time, meaning all it was basically it was dynamics related. It was related to the dynamics of how the cutting tool system works. But we kind of had to move on from there to a little bit more physics oriented models. So when I moved for my PhD, I really wanted to go to a department which was very strong in engineering mechanics. So there were various options left to me, and I chose Penn State. And at Penn State, it was a joint venture between School of Engineering Mechanics, within the College of Engineering, and School of Industrial and Systems Engineering, or rather, it's called Industrial and Manufacturing Engineering. So a very strong thrust on manufacturing at the time when I was studying there. Pretty much almost all the faculty there were in manufacturing area. They hardly ever did. They had like about a couple of people in operations research and a couple of people in human factors, and pretty much everybody else, about 20 of them were in manufacturing. So what we ended up doing is we started looking at how we can use the heat and the mass transfer models, right? So the heat transfer model, a transient three-dimensional heat conduction model, basically the differential equation, which is a partial differential equation in 3 space dimensions. And then it is also a second order partial differential equation, and also has the time dimension, which is the standard heat conduction equation. And we used a lot of the convective boundary conditions, which were going to be supplied through the actual process itself. So we wanted to do the sensing where the sensors are providing data as boundary conditions to this heat transfer model. But that didn't do anything to the transfer of material, which is basically based on diffusion and abrasion. So we created the Archer's wear model and also the fixed law of diffusion. So we had to solve 2 simultaneous differential equations, one for mass transfer and one for heat transfer. And so that was my dissertation, where the boundary conditions for one fed to the other, and so on. And what would happen is, so that is, if more material goes away, then the temperature, there is a smaller volume of metal or a lot smaller mass that was taking away the heat. So we had to keep modifying it. The model had to be kept refined multiple times. And this was at a time when you use Fortran code and writing these finite difference and finite element models, which took forever to compute. But in a sense, what we wanted to do was come to a way that we can do toolware monitoring online using some physics-informed processes, such as using heat conduction equation and so on. So we did that, and really I moved to University of Oklahoma in 1988, actually. So I was still working on this research for a little while. But the main problem was that most of the equipment I had at that time was all equipment that I owned, which was on loan from Penn State, even when I came to University of Oklahoma. So I had to kind of have some stopgap till I built my own equipment. Remember, this was at a time when they hardly gave you any startup money. So there was no startup money involved. So I basically had to build my own, so if somebody asks me, what's your biggest contribution in your mind, I would say that, hey, I have a little over $2 million worth of equipment in my labs, and that's all completely through research grants and through partnerships that we have been able to procure. Not one penny was given to me to build my labs. So, I mean, even now, all the maintenance of that equipment is all done by research money, which I generate. So, I mean, it's kind of no modest way of saying that, but it is also my sense of pride. So in the meanwhile, we modeled how do you model the process, numerical control process and how do you do path planning. We worked a lot with tolerances because that is a very important issue in developing precedents for process planning. How do you develop bill of materials? Some of these work, which is kind of softer, and NASA funded that work, and also NSF. We also set up a lot of, we also made setups for computer vision, which we'll talk about in terms of metrology. So metrology, really, measurement sensing has been integral to my work from 1985 to now, right? Actually 1983 to now, when I start my master's to now. So somewhere in there, there was a fundamental pursuit of how do we model friction, and friction, friction laws, Coulombic laws of friction do not work in machining because of the high normal loads. And we wanted to develop boundary conditions because we did not have good, accurate boundary conditions for our wear models or our temperature models or any of this, mainly because you can't assume Coulombic friction. A lot of the friction that happens in a machining process is what is called a stiction or seizure. So we had to model the ranges where seizure is promoted and where sliding is promoted. So it's like basically two things that are happening. Now the domains of these, you have to somehow try and find out where does sticking happen, where does sliding happen. There are some classical models from the 50s and 60s where they say, hey, the sticking would happen in the front part, and the sliding would happen in the back part. But that is not very true. When we did a lot of experimentation, we found out that the sticking can really happen in the back and sliding can happen in the front, especially in machining of aluminum, in kind of very adhesive materials such as aluminum. And mostly we were machining things like aluminum 390, which is basically a cast aluminum, which is also very abrasive because there's large percentages of silicon. And so we ended up modeling some of these things, the seizure and sliding boundary conditions, which could now act as input to some of our toolware modeling. So now we combined that along with this NC path planning, where we say, okay, in interrupted cuts, how does this work? How do you take a cutting tool, and how does a cutting tool exit and enter? And based on that, how does the tool wear pattern happen? There is also a fracture. You got to superimpose fracture. There is gradual wear. There are multiple things that you have to start thinking about. So all until 1999, I was really in this, and we were trying to study the surfaces that are generated. And the surfaces that are generated was more the full surfaces, as well as microscopic elements, which are deemed as roughness and waviness in machining, which that's how we started. We started using, reflection. We tried to take out the specular part of the reflection and used computer vision to study the diffuse part of the spectrum. And we actually mounted cameras that will just capture the spectrum themselves and then do some statistical analysis on it to try and find out the slope irregularities on surface. That is, we characterize surface roughness using slope irregularities rather than height irregularities, which is normally done using all those values like RA, RQ, and things like that. So that led to our bigger problem that, hey, you know what? You really cannot be measuring local areas of surfaces. You have to measure the whole surface in order to try and find out what the impact of the process on the surface was. So that's when we really got into coordinate metrology. And that's an area which I have kind of kept from then to now. So in 2002, we really went from surface metrology. In addition to surface metrology, we were doing coordinate metrology, which was basically the entire surfaces like spheres, like torus geometry, cones geometry, cylinders, flat planes, and so on. Now, remember, you got to worry about the process. You got to worry about the product. You got to worry about the features of the product. And that's where all these things all integrate, really. So you are measuring forces in the machining process, and measuring temperatures in the machining process, and measuring acoustic emissions. Now, all these are really telling you, hey, your surface is really going out of control. And use that now in some way. Use your path plan. Say that, okay, the tool is exiting out here. That means there is a sudden reduction in the load. And so what you're expected to see is these corners are possibly going to be warped, or there is going to be burrs on the outside part. So you study the process with regards to the product itself, and then you sense it. you somehow take all that sensed data from the process, and then you look at product data. Then you start merging both the product data with the process data to try and find out what can we do now to the process such that the product does not come out flawed. So this is the area that we worked on a lot for almost 20 years. I mean, going back and forth, back and forth. So it's a kind of a very iterative, very recursive, whatever you want to call it, but it was just going back and forth between the process and the product, which kind of evolved into reverse engineering, which is basically a lot of the work that we were doing earlier was that in aircraft sustainment. So in 2000, in 2000 summer, I got a contract with U.S. Air Force, and one of the things that we ended up doing was that we wanted to start doing reverse engineering, which is maintaining airplanes, and I'm going to talk about that in my next few slides. So I'm not going to go in there too much right now. So we started doing reverse engineering in addition to product metrology. Now, product metrology, process metrology, and reverse engineering all together. Now, remember, almost all of these things were happening where we are trying to do this part, the front part, trying to diagnose what materials are being worked on, what is the geometry of that parts, and so on and so forth from the reverse engineering angle. Are they meeting specifications based on from the product metrology angle? And then, hey, you know what? Are we using the right kind of parameters in the machining process? That is basically, are you using the right kind of bill of materials? Are you using the right sequence of processes in order that, you are making the right part? And then, hey, you know what? Are the forces and the temperatures all kind of working hand in hand with that? So all this kind of combined right now. Then we found out that there was somewhere in 2016 we got a large NSF. So most of my work was supported by NASA, U.S. Air Force, and also National Science Foundation. Several grants from National Science Foundation. Up to 2008, there were a lot of grants, almost 12 grants from National Science Foundation, about 6 to 8 grants from the U.S. Air Force, and about several industry grants also. And then several, everybody was interested in the same set of things. Like, so we ended up having a lot of funding for some of these things. And U.S. Air Force directly from AFMC, which is from Dayton, Ohio, we're funding and supporting a lot of this research. Then we realized that one of the bigger problems was that, okay, we can do all this research, but for mission-specific projects, how do you empower small manufacturers? How do you empower small manufacturers such that they can do some of these things? How do you educate them? And then how do you empower them, right? So that's where we moved on from 2016 to currently. We say that how can we access what is out there that is shared free and bring some of these things into a digital world and start connecting small manufacturers with big manufacturers and or directly with the prime, meaning directly with the source, which is typically U.S. Air Force, U.S. Navy. We have worked with both Air Force and Navy. And how does that work? So that has really ended up becoming my research now. But now I have never changed my roots. I've worked about all until now. Majority of the work I've done is in subtractive manufacturing, as it is called today, which is in the machining enterprise, right? So we worked with forging and we worked with casting, investment casting, precision forging, and machining, largely machining. So we have worked with deformation processes largely, not as much solidification processes. Casting was kind of, we really never studied solidification in casting. So we really can't claim that we have worked on solidification as such. And so the transition happened here, somewhere here, that some of my students were started working in additive manufacturing, and we built, we had a chance to build, a dinosaur for the museum. We were able to build human jaws using Ti-64, which is a titanium 6Al4V, which is an alloy, titanium alloy, which is a bio-neutral. It's an osseointegrating material. So we worked with them, and we started doing some additive manufacturing. We started building porous scaffolds of some of these things using a process called electron beam melting. So my first exposure to electron beam melting was in 2008. When we were doing Air Force work, we ended up doing some biomedical work. And somewhere there, I kind of said, hey, you know what? This might be really promising for us because you really can't do internal geometries with machining extremely well. So, however, the accuracies and the precision are still much, much better than additive manufacturing. But metal additive manufacturing was what I was interested in. I was never interested in plastics because I don't think I was qualified to study plastics. So I was interested almost entirely in metals. And as luck would have it, the University of Oklahoma, under the leadership of Ingtav Liu and Zahid Siddiq, we were able to go in that particular direction. We were able to buy two large metal additive manufacturing machines, one to machine Ti-64 and one to machine 17-4 stainless steel, precipitation hardened stainless steel. Both of these materials I've had a struggle with in machining. But then, however, after we have hired several people now for that enterprise, and I thank the team, the SAML team, which is the Sooner Advanced Manufacturing Lab, where I've been able to kind of transition a little bit. I shouldn't say that I claim to still be an expert in that area, but I've been able to transition to additive manufacturing and seeing the full benefits of some of those things. Now, Inconel 718 is another material which we are trying to get into, which is again an aerospace alloy, which all of us are trying to get into. Now, I know that I kind of tried to change the flavor a little bit from the last time, so I'm not going to go here. I won't go into this slide either. I will go directly to reverse engineering since I talked about reverse engineering. So reverse engineering or shape engineering is really required whenever an industrial part or an assembly ceases to perform as intended during service, right? And this happens a lot in the cases of the reverse engineering happens mainly because aircrafts that were supposed to be decommissioned. I'll give you a small instance. Tinker Air Force Base here, which is the largest employer in the state of Oklahoma. They have an airplane. It's a stratotanker called KC-135. Anybody heard of this KC-135? No. Any of you from here in the audience able to know of KC-135? So KC-135 is a stratotanker. This is an airplane. Can you all hear me, by the way? I'm suddenly lost the pictures of all the people.
Yeah.
Okay. So yeah, KC-135 is a stratotanker. It's called as a stratotanker. It was built in 1957. What you can do is, while you're flying in an airplane, you can lower a boom or a hose pipe. And I have actually had the opportunity to do that, where another airplane is coming within 500 feet of it. And then you have a chance to actually pump fuel into it, okay? So we did this in 2014 or 2015, I had a chance to do this, where you actually get into at a certain angle, and then you fuel an airplane in air so that the airplane doesn't have to land to get fuel. So this is a marvel, but of course, remember, it was built in 1957. Most people thought that it would be dying by about 80s or 90s. However, the US Air Force said, hey, it's a unique enough machine. We should keep this going for several more years. So it has actually been commissioned to 2040 now, right? Same thing with B-52. 1952 is when it was built. Some of those old carriers are now currently being used to this day. So what is a big thing about this is that you can't go to AutoZone like, you have a spark plug that you need. You can't go to a store and just buy one. They don't stock these air parts. No two airplanes, pretty much, not even the same model and make from the same shop, from the same company, are alike. So most parts are built one time. And for a specific, can anybody guess, in a commercial airplane called a 747, which was recently discontinued for production, which a lot of you might have flown in. Hello? Hello, can you hear me? Hello?
Yeah, we can hear you.
Yes, we can hear you.
Yeah, no, I'm kind of getting a lot of background noise, that's why. Okay, anyway, so the 747, how many parts do you think it has, a 747 airplane? Many of you have flown a 747 transatlantic flights until this year so far. Although they have stopped producing them, they still are flying them. Lufthansa flies them.
Maybe upwards of 10 million.
Yeah.
About 1 million individual parts, not counting fasteners. So there are totally close to about 3 million individual parts in there. And these all have to come together. Now, some of these parts might have, they came from maybe 20,000 different suppliers. Are you also hearing some background noise? Everybody hearing background noise?
Yes.
So yeah, okay. So anyway, so when it comes from so many suppliers, a lot of those suppliers have gone out of production. They don't make those parts anymore. And you don't know what part is going to fail. And most of the time, you are maintaining things which are critical parts, like the engines are maintained very meticulously, the landing gear, things like that. They are maintained very meticulously. However, there are like something that is inside the airplane. There is a control, there is a bathroom door, maybe there's a door latch. Uh, there is no way they're going to store backup parts for these. So when they become important, when it comes to a time when you have to do sustainment, it's called as aircraft sustainment, is whenever they want to maintain aging aircraft, they got to get those parts at the maintenance stage. Sometimes they are diagnosed right at the maintenance stage. Sometimes they actually break, and now you got to go and find that part. And the important thing is the lead time is very, very large to supply even like say a door latch, for example. You could be doing, I mean, like I'm exaggerating, obviously. You could take 9 months at a cost of $500,000 to replace a door latch, so which would be considered quite difficult, especially if you have to keep flying and you really that is an important part, not a critical part to the flight, but then it is an important enough part. Then you have to try and come up with the original equipment manufacturer sometimes doesn't even exist. You didn't even, sometimes these parts lasted 20 years. Some other parts lived and died in 3 months, but then some parts lived for 23 years. So I have not replaced it in my lifetime. So all of a sudden I'm trying to replace it. And that's when reverse engineering becomes very important. So what you have to do is now you got to find the material, then you got to find the geometry. So that's some pictures I'm showing here. Some of these are things which we have reverse engineered. I mean, including for Federal Aviation Administration for a surveillance truck, which happens at the borders, which basically does a lot of surveillance. That was basically a Ford chassis, and people keep building sensors and things like that to it. And the final product, the Ford, none of the people actually got to see the final product. So we went to the borders in Arizona and scanned that, and we created a 3D model of it. So what you do here is that you acquire the data using what are called as point clouds, and then use that, create boundary representations of it, and then eventually make it into a CAD model. Then you have to try to make it into an STL file so that some manufacturer can actually make it. And so this is where the democracy comes in. If you can do the front end and give a STL file, you can share that STL file, then whoever is capable of making it should be able to make it. That's the big part of this whole democratization process that we have been trying to do for the last 10 plus years now. And now almost fully we are trying to do this, is that we say, hey, you know what? I can give you the full CAD files for this part, and I can give you all the slices. I can give you the whole geometry. Now, if you have the capability to take that CAD file, and if you can make the part, then hey, so be it, right? And Air Force itself wants this, right? They want various levels of abstraction, and we are able to generate CAD models out of parts, right? And it's not just the geometry, you have to also worry about materials. When you do reverse engineering of materials, you got to do things like energy dispersive spectrometry, which is basically using, first you use a scanning electron microscope, and you use line scans, and you try to find out the elemental compositions, then you match the microstructures with the original microstructures, and somehow try to find out. Now, there are some challenges, right? So you can't necessarily easily find what was the heat that was given. So was it cold forged? Was it heat treated? And how was it heat treated? Was it annealed? Was it tempered? I have no idea. I mean, like, this was done 55 years ago. I have no idea how those parts would have gone through, what they would have gone through. Now I got to divine all that stuff and come up and supply all those so that they can make a replacement part that will go on that airplane. So this is the big part of reverse engineering that we are doing. We continue to do it. I right now have at least 3 projects that I'm working on reverse engineering. So these are various types of equipment which we have in our labs, right? So we have a Faro photon scanner. This is called as a Leica scanner. This is one of the most expensive equipment. This is a Leica scanner, which can actually give you CMM level accuracies. This is coordinate measuring machine. I have multiple ones of these. I have a carbon fringe interferometers. I didn't put all my things in here. This is the latest one that we purchased called the Kian scanner. We have a Faro arm, which is Zara, who is attending this seminar. She is now an expert on Faro arm. So she has been doing this for a company project right now. So these are some of the sampling of the equipment that we end up using, right? So coordinate measuring machines are very time consuming because these are contact. A lot of these other equipment, they're not contact measurements. They actually can generate larger point clouds. However, they have nowhere near the accuracy of a coordinate measuring machine. Okay, the coordinate measuring machine uses a touch trigger probe, and so you can get a micron accuracy. Some of these other equipment can get anywhere from 10 to 1,000 microns. So metrology and inspection follows the same equipment, right? So mostly product metrology follows the same equipment. And so we have robotic arms, we have various types of devices. And here what we do is we verify the form and the geometry of parts. And we try to see for conformance. Conformance is the part meeting specifications? When you're making something, have you made it to specification or not? That is done using what is called as form and geometry verification. And then you have to do surface roughness evaluation. You have to do tolerance evaluation. Then we also use adaptive methods because we have knowledge of the process. As long as we have knowledge of the process, what we can say is, hey, you know what, this was this particular process. Say, assume that I was using a machining process and I was holding it in a fixture. That caused a certain deflection, such that the central part was actually, there was a cave in the central part. So then what I say is, hey, you know what, I'm not going to necessarily go in there and look for a maxima. What you're going to likely to find is a minima in there, and the maxima will be possibly at the sides. So things like this, that is the adaptive methods. When we are scanning, when we are measuring using coordinate measuring machines, when you are getting to finer and finer precision, you have to try and make sure that you use all the knowledge about the process as possible. And that's what we have done a lot, is how do you integrate processes with the products, right? So that is metrology. And sustaining legacy aircrafts, one of the important things here, which is the remaining useful life. They do a lot of FMEA analysis, various things such as corrosion. You got to model corrosion, material predictive analysis. Until about 5 years ago, University of Oklahoma had nobody who worked on metals or ceramics. And that was a big crippling point for us in bidding on aircraft contracts. Now we have several people in AME and in chemical that have worked on some of these topics. I'm sure that there are a couple who are actually attending this seminar. Then, other thing is that how do you supply chain source, right? So and how do you qualify? This is a very big problem, right? Air Force is not obligated to accept anything and everything you supply. You have to come up with, at some point in time, you got to say, hey, you know what? I made this part. Do you think you will be able to use it? And at that particular time, they say, no, I'm not able to use it. Then basically you are stuck with the cost of having produced it. So you got to really work with the engineers in the U.S. Air Force engineers, U.S. Navy, whatever you're building for. We have worked for Army also, Navy also, and Air Force also in building various things, right? Whether it was a surveillance truck, whether it was a watering fueling tank, whether it was a ground vehicle, it was an aerospace, flight vehicle. We have worked with a lot of, with Choctaw Defense, we worked on a lot of land vehicles. So asset lifecycle management using model-based systems engineering. And that is a topic that someday we will talk about if you want to come in and discuss it. And then again, advanced manufacturing, which most of you are familiar with, additive and subtractive manufacturing. Really in this realm, in the aerospace realm, forging and machining was the combination, which was the method of choice. And this kind of just gives you an idea. This is the Clark Air Force, which David Boren used to fly when he was at it's a turboprop. And I basically scanned it, and this just kind of gives you a clarity in terms of how many individual data points that we scanned. And we typically triangulate it in order to create a boundary representation of it. So this is just to kind of give you how many points you can generate using, like I use the Faro photon scanner. We generated close to 10.2 million points on it. So anyway, so I guess, so I'm giving a really superficial or, higher level treatment of this, but, we can do a lot of these things. We can do predictive modeling of metal parts and things like that. And a lot of this work we have done in the past. So where is our big problem? So I think the biggest problem that we are having is that is the manufacturers and the designers hardly know each other. So there is a lot of needs that get generated in a lot of realms. I mean, we are focused almost entirely on aerospace and defense. However, in automobile world also this happens, and in other industries this happens. Designers are trying to find manufacturers. Manufacturers who have capability are sitting out there, cannot be found. Now, a lot of these, I mean, remember one thing: 75% of the U.S. manufacturing that happens manufacturing in the US, 75% of it happens with where there are 20 employees or less. Okay. They don't have large advertising bills in there. They don't have large advertising budgets. So they're not going to even have a web page. So you cannot find them. The other thing is, I don't know, there are a lot of registries like Thomas Registry and so on, where you can actually go and try to find a company, but then they don't even have money to go into the registry. So that means you really, you got to know these people. It is word of mouth and word of mouth only. So how do you make all these people meet? And so we have been working with multiple different agencies to try. I mean, we have worked with NIST on this. Is how do you try to? They have a program called Manufacturing Extension Partnerships, and one of the things that they really came up with was what is called as a MT Connect. I know some of you are working on MT Connect in this group here. And so this way you can try to find out what the manufacturing capabilities of various manufacturers are, somehow try to find a way to connect them. So how do you find the designs? And so that is where the open area networks come in. So what ends up happening is a designer says, find me alternate designs for my Greer sprocket. The designer says, another designer says, find me a manufacturer that can produce my designs. And another person says, I have found several qualified manufacturers searching for designers just like you. Can I connect you with them? And this is the area, the match finding is what we want to try and do. So how do we do this is basically we use online directories, open knowledge directories, such as things like GrabCAD. How many of you have heard of GrabCAD? No, I'm just trying to get a screen where I can see all of you again, and I'm not able to see. I don't see anybody. So,
I haven't heard of GrabCAD, but something different that I use is OnShape. It's similar where you can.
yeah, it is a similar.
share.
Yeah. So if there is a company called Exometry, anybody heard of Exometry?
Yeah, Xometry. Yeah.
Okay. So what happens is this GrabCAD gives you a lot of designs, CAD models for a lot of designs. So you can create a string. I mean, like it's basically a data matching. It's a string matching. All you just go, you create a string and you can go and find your part, the variant of a part. Okay. Mostly it's all exact geometry. Most of the GrabCAD is exact geometry, meaning there are no tolerances tied to it. So you got to tie the tolerances to it. That's easier said than done. You got to make tolerances, and then you got to try and find out what quantities, the required quantities that have to be made. So one thing about auto industry is you have tens and thousands of parts, whereas in aerospace industry, you have one part. A lot of times in aerospace repair industry, you have really only have one part. That means you have no notion of tolerances. How can you do geometric tolerances? How can you do statistical tolerances? It's almost impossible for you to try and define that. And that's where the big challenge comes in. So we have to act as a conduit, take that GrabCAD model, come up with the tolerances, and add the tolerances to the design, and say, now who can make this? And so based on the tolerances, you can identify the capabilities of multiple manufacturers who can deliver, right? So it's like, it's always a capacity building exercise. And you have to always understand that there are X amount of manufacturers that can produce this tolerance, this surface finish. And then you got to be able to give them that product. Remember, they assume the cost, especially if it's Air Force or any of the militaries, and they assume the cost if it is not taken, it is not accepted by Department of Defense, right? Whichever agency of Department of Defense. So there are multiple ways. I mean, like, so we have worked with DLA. I mean, right now we are working on a project with Defense Logistics Agency. They do a lot of reparables. Then there are other wings which are called 448 wing, 848 wing, and so on. They do replaceables and reparables. So you got to go and work with that specific agency, and then you got to connect the small manufacturer with that. There has to be a central dispatch area. Lots of businesses cannot be found. Metal fabricated industry is a $338 billion revenue annually, okay? And 2.7% is the marketing spent by small manufacturers. They really cannot afford, so they cannot be found, right? Oklahoma is no different. Oklahoma is much less than 2.7% actually currently. So which is kind of creates a big problem. American manufacturing highlights the importance of rapidly identifying manufacturing capabilities that exist out there. Millions of 3D CAD models already exist out there openly, right? But there is no easy way to search for them and no easy way to add tolerances and those kind of information, which is called as annotational information right now. They are textual, almost entirely textual. So if people add plus minus 0.03 to it, or like a feature control frame, which determines the form tolerance or the geometric tolerance, the orientation tolerance, parallelism, perpendicularity, or like true position, concentricity, whatever you are trying to add to it, there is absolutely no way that there is any geometric identification of that, or there is any geometric understanding of that. So you got to add it annotational to an existing model that exists somewhere else. But these models do exist. Now the supply chain diversification is from local to regional to global sourcing of alternate suppliers. And this is a big, huge, humongous challenge right now. Is that how do you find all these manufacturers? Now, there are two manufacturers. They could both be competitors on one project, but then you want them to be collaborators of another project. How can you make that? How do you protect their intellectual property? It's like a lot of these shops have like three people. There is like a dad and a daughter. I mean, I know a company which I use a lot. The daughter is a machinist. The dad does everything else. He was the machinist at some point, and he does all the purchasing, the sales and everything. She is the machinist. She is the only machinist for that company. So really, the manufacturing industry, it's a 10% GDP, right? Somewhere in there. And where are the companies actually? The US manufacturing really still, so 11% of our GDP is manufacturing companies out here. Manufacturers contribute 2.3 trillion to the economy. If you really look at it, there are less than 5 countries. It's actually the 6th largest economy in the world, just the manufacturing industry in the United States. So a lot of it goes into defense. And so that is why a lot of our work has been in defense and in aerospace. But there is also a significant part of it in the commercial world. You see that a lot of the auto manufacturers have actually made an entry into the United States. A lot of auto cars were in the last 20 years or so, Toyota, Honda were all having a big building manufacturing presence in the United States. Volkswagen, BMW, and a lot of big people are building in the United States. Now, if you see Rolls-Royce, they are building engines, aircraft engines. They are the second largest engine manufacturer. Aside from GE, they always keep fighting hand in hand, right? I mean, like they go one over the other, GE, Pratt, and Rolls-Royce. Now, these three manufacturing companies, there is a huge presence in the Northeast for all three companies. So the small manufacturers, however, are the ones that are supplying to a lot of these people, whether it's an engine part or whether it's an airplane part. A lot of the manufacturing happening in the small states. Now, I've just kind of, there's a small graphic here. If you see that a lot of the manufacturing migration is actually to the eastern part of the United States. Oklahoma is prime for growth in this particular area. So that's what we are trying to help out. Now, actually, what happens is manufacturers exist, they're not found. The growth, so how do you empower these people to grow more? So how do they find, say, if suppose their capacity is filled, I mean, their capability, assume that they have capability to build something and their capacity is filled, they're going to give it to somebody else. That somebody else also does not exist. How do you create them? That is the thing that we are trying to work with NIST on. So anyway, so I guess in terms of top 10 manufacturing sectors are machinery, fabricated metal products, and so on. Now, if you really look at it, aerospace products and parts manufacturing, look at for growth in Oklahoma, this is the area that we are going to grow because we are right in the middle of what is called as the maintenance, repair, and overhaul capital of the world, right? So we're right in the middle of that. So it starts somewhere from Wichita, Kansas, the NIAR, I mean, those of you who have not heard of it, National Institute for Aerospace Research, one of the largest funded centers that is affiliated to the university, which is Wichita State University. From there, if you go all the way to San Antonio, Texas, that is one of the 3 corridors of maintenance, repair, and overhaul, and one of the most productive and expensive corridors also. So, and Oklahoma resides in here. So where is the biggest chance for growth? In aerospace products and in machinery products. So what are we trying to do? There was the total output for manufacturing was 19.13 billion in 2018 here in Oklahoma. Average of 138,000 employees, manufacturing employees in 2018. And why I'm quoting 2018 numbers is I don't have more current numbers. And this goes into specific industry, how many manufacturing states and what their industries are, what their manufacturing presence is. And some of these things are basically, so how do we create these service listings? Service listings cost money, right? So this, like I said, Thomas Registry, you don't really, I mean, you want to be able to populate like this. You want to actually go in there, say, this is what we make. And if there is a way that we can create some kind of a tree, and we do some tree pruning algorithms. So this is kind of a more systemic model. You see, you have physical components which have to be maintained somewhere. There is measurement and scanning capabilities that have to be maintained somewhere. CAD capabilities, specifications, manufacturing specs, post-processing capabilities, inspection capabilities. If there is some way we can kind of write to a model-based file and create a singular truth, then a lot of people from multiple facets can actually come in there. So how it would work is that there is a data lake for design files, design development center, a procurement authority, which will go into a search system, a manufacturing database, and then you're supplying to a group of small companies, right? I think I know I'm up against time. So I will basically not talk about this use inspired R&D and all that stuff. Translations. I mean, you have my slides, and these are more pretty straightforward there. Product designers, we want them to have to spend less time, energy finding design assets and manufacturers. So quicker speed to market. Manufacturers have the ability to be reached by newer clients. I mean, this is a big problem right now that they don't know how to do that. And because they don't have that connections. And then Oklahoma and its neighbors, ability for in-demand products that solve a need to enter the workplace. So really, that is my pitch here. And I will go from here to answer questions. I know that I possibly have lost most of you. I didn't have the screen on. But yeah, so I know that I kind of pushed through some things a little bit more and deliberated on some things which were possibly, maybe I should not have, but this is where we are. I would really appreciate any questions that you have. I know that a lot of you have a lot of interest in a lot of the topics that we talked about. So if you have any questions, we'll be glad to share.
I would like to ask a question, if that's okay.
Yes, sir. Yes, sir.
Thank you for the presentation. I really enjoyed it. So I'm going to ask a couple of big picture questions. So since we have...
Is this, are you talking from a very crowded room?
Yes. I'll try. I'm at a Starbucks. I'll
Yeah.
try and go outside and see if that helps.
No. This is fine. This is fine. This is fine. Yeah, just keep your volume up a little bit. I think that'll be okay.
Okay, perfect. Hopefully this is slightly better. So I had a big picture question. Given that we have all these, wonderful scanning techniques that generate so many points, data points, and then we already have such large depositories of CAD models, how much of a need do you see for CAD technicians in the next, 5 to 10 years or so? Yeah, that's my question.
Yeah, so yeah, that's an excellent question actually. So the translation of taking, the scans, conversion of scans to CAD models is not simple. I mean, and Zara can tell you that. She's working on a project right now, and that is one of our biggest challenges. I mean, like I've been working on this project for 25 years, and still the biggest challenge is how do you take scanned data, how do you take point clouds, millions of points, and try to create an accurate CAD model. So that is step number one. Right. Step number two is how do you take that CAD model and make it into a manufacturable file? That is model number two. That is problem number two. Both of these are big problems still. So there is a huge need for CAD engineers that can take it to from a point cloud stage, right? So we use software like Geomagic and things like that. But There is a huge need for us to take wireframe models, convert it into boundary representations, and then create it into full solid models, and then create variational geometry of it. So the CAD people really have a huge business there just in creating variational models, right? So we don't have anything variational. Right now, everything is exact geometry. So the dimension-driven geometry doesn't happen. So if I tell you 2 plus or minus 0.2, ask a CAD system to interpret that. That's a big problem right now.
Right.
So that is a huge challenge for CAD engineers right now, is how do you incorporate information that is geometric information, which is variational geometry information, more than just being annotational, which people did even in the drawings that many of us in my generation, we had to make physical drawings, right?
I
Engineering.
started from drafting too, yes. Yeah. Thank you so much, Shiva.
Thanks. People are itching to be done.
Dr. Roman, it was a great presentation. I really enjoyed the topic you discussed. One question I have, especially one important thing would be when you go and you do a scanning, then maybe a revised version of the component. If you use additive manufacturing, in many cases, you may come with an idea to reduce the complexity of this component. Do you do that as well? Or what is the kind of, if you work with industry, do you have that permission to refine the product or maybe use kind of maybe some simple equipment that can do the same things?
Excellent, really excellent question. So this is a major struggle. I'll tell you, you cannot make design mods drastically. Sometimes, if a part is deformed, the assembly around it is also deformed. Okay. I mean, if this is not even changing anything to the product, the assembly is deformed. Now you take and make a good part and you supply it, it doesn't fit that assembly. So unless you want to replace that entire assembly, making just one part is not going to help you. But then now you have an opportunity. You can replace that entire assembly. You can modernize it. So they have changed. I mean, Air Force has changed its mantra from, or Department of Defense has changed its mantra from maintenance, repair, and overhaul. They're calling it modernization, maintenance, repair, and overhaul. The MMRO is what they are calling it. But the bigger, it's easier said than done, because some of these in aging aircraft sustainment and asset management system, the big problems is you have millions and millions of parts. You cannot modernize it to a point. Significant modernization cannot be done, or like change in designs cannot be done, because it will not fit something else it was supposed to fit, right? So this is a big issue. I mean, like, we can do design mods. We can easily do design mods because like you said very correctly, a lot of those appendages that we used for some reason may not be even relevant anymore. So we could change that design entirely. And then some of this complexity could be changed drastically. But then, hey, and you can also add complexities where you possibly don't need two parts. You could be doing a singular part which does both parts together, right? So you have all these things that are available, but then you got to worry about the rest of the parts in that assembly. And that's where our bigger problem is. And sometimes exact geometry, when they tell you, like DLA gives you a geometry to replace, they are going to expect that to be exactly the same spec, because this was an airplane that was built in 1957. I mean, Tinker's biggest business in Tinker is KC-135. And if you really look at it, that's got all these parts. I mean, like, they do some AVACs, they do some, C-130s, they do some B-2s. They don't do B-2s, actually. They do B-1s, B-52s. And if you really look at it, all these airplanes, all these different old airplanes have this issue. You're going to have really old, I mean, AVAX is a prime example. Now, if you remember, I mean, if you have been inside an AVAX, you would know that almost entirely that avionics, electronics has been completely changed now. It's completely changed now. So unless you do wholesale changes like that, right? The frame is still the same. It is still a 707 chassis. AVAX is still a 707 chassis. I mean, like, Boeing discontinued 707 how many years ago? So, I mean, that thing is still flying and protecting.
Thank you so much.
Thank you.
Thank you, Dr. Raman. So any more questions from the audience?
Hi, Dr. Raman.
Yeah.
It's nice presentation and nice to know the reverse engineering. That I have question that once you do the reverse engineering, do you how much you can recreate that material from the original version?
So good question. I mean, so how much can you recreate? Meaning you are going to lose some accuracy, right? Certainly, because
Yes.
you're scanning it. You're scanning it and you're only as, I mean, like, remember, you're only as precise as your measuring instrument tells you. That means the least count of your measuring instrument. And this is what I tell you in my undergraduate classes. The least count of your instrument that you use to measure determines what you can make and what you can design, right?
Okay.
So you are going to lose. So if I use a vernier caliper to look at a shaft, right, measure the diameter of a shaft, and its accuracy is plus minus 0.01. If I use a steel rule, it's plus minus 0.1. If I use a coordinate measuring machine, it's 0.301. So now, if I use an atomic force microscope, possibly I can get several more decimal places, but still there is a finite least count. And you're not going to use an atomic force microscope to measure the diameter of an engine, right? So what ends up happening is you're limited by the equipment that you have for measuring it. And manufacturing capabilities have improved certainly over a period of time. You can build parts more precisely and also more accurately today. But then the measuring, you're still limited by what you can measure. So there is going to be a lot of times you scan something, there is going to be some loss in accuracy, right? Hopefully you're not any loss in precision, but you're surely going to have some loss in accuracy. And accuracy meaning hitting the target, right? So precision is just basically the range. So those are the tolerances, the repeatability.
And also the modern technologies with integrating with the old aircraft system. So is it very difficult, or how do you overcome that challenges that integrating modern?
So it depends on what you're saying, modern technology, right? So if I say what was called ultra precision machines, right? In a machining process, what was called as an ultra precision machine, like Rank Nemo used to make them, $450,000. That is done by a lathe I can buy for $45,000 today. Okay. Ultra precision of then is precision now. Precision of then is basically not in existence today. So yes, we have progressed in that way. Yes, absolutely. Manufacturing capabilities have certainly changed. So can we make better parts? Can we use that technology to make better parts? Yes. I mean, are the guideways, do they have less play? Yes, they do, right? Some of these guideways on these things, previously there used to be a wobble. I mean, I don't know if you have used older machines. You can actually, your cross slide and your saddle will, you can move one on top of the other physically. There is that much level of backlash and so on, all the errors. But today, those are all kind of electronic. Those are all electronic. The technology exists today, yes, but we are still building an old airplane. Remember, we're not really, this is, if we are building a brand new airplane today, that's a different thing. Making every part new, yes, that's completely different. But you're trying to fix an old airplane and going to keep it alive. That's where the issue is. I apologize. I haven't seen I've not seen any of the things. Okay, so I think a lot of people are just telling me that they're jumping somewhere else. So that's good.
So let me join in the conversation.
Uh-huh.
In India, one of the things that I proposed during my sabbatical was, in essence, bringing in micro entrepreneurs. And these micro entrepreneurs could be machine shop people, could be people who do handicrafts, anything,
right,
into the supply network. First within the region, the state, then various states in India, and then into the international market.
Okay.
Now in India, they have a tier one company. They have the OEM, which is the car company. Then a tier one companies. These are the people who are aggregators. These are the people who go around and they find these people who 1 or 2 person companies and stuff like that. Those are tier two companies.
Right.
And so those tier two companies get contractually obligated to the tier one companies.
Correct.
Who then deliver it to the OEMs.
Right.
So this model has been implemented for the automobile industry in India.
Right.
And there is potential to expand this model to handicrafts, to other domains of the Indian economy. And so what you're talking about is very appropriate, particularly for developing countries.
Well, the one thing is that, okay, so there are these establishments which connect the primes to the subs, and the subs can be any level of sub. So this tier one, tier two that you're talking about is in some way, and I chose aerospace and defense because that's the industry I work the most with. But aerospace and defense industry does work quite a bit different than the auto industry. Auto industry, most of their supply chain is reasonably well established. Okay, I mean, I don't want to say that they know it and so they're ready. They don't ever need to change their supply chain. That's not what I'm saying. But their industry is reasonably well established industry. Profit markups in auto industry is very, very small. 6% is your band, where you can do whatever. You can put a rocket in your car, but you can still mark up only 6%, and you got to still match competitors. Aerospace, there is no sky's the limit. I can spend 10 million over the budgeted expense. I'm still okay. So that's why you have a lot more things to, I mean, like people are willing to wait for longer lead times. People are willing to pay more money. People won't compromise on quality. So they say, okay, you know what, deadline, if not this March, maybe next March is a lot of times gets pushed like that. And so the establishment of that supply chain is very, very, very different. And it is also very difficult. So you might know a lot of manufacturers, and then there are other manufacturers you do not know. How do you connect all these people? That's where the biggest problem.
So I hear you, Shiva. What I'm saying is that once you're established, you got this thing going here, the software that you put together, the model that you put together has potential application in India. That's all I'm saying.
That's good.
And you've done it for aerospace, so the domain information is of no value.
Right.
What is of value is the service that you're able to provide using the framework that you've put together.
Correct.
So, for example, you could have your Indian student, Pravesh, or whoever it is, going back to India and starting his own company and being an entrepreneur to make this happen using your technology.
Right.
So what I'm getting at here is that you're creating a service, a tool for a service that is generic and can be replicated and used in India.
Right. It can be. Yes, certainly. Thank you. Thank you.
So Harsh Parmar, you may like to think about that to take this tool or this software and all this sort of stuff back to India to make it happen. Himadri, the same thing for Bangladesh.
Sure, Dr. Farooq. Yeah.
So I think focusing on the software part of it that is transferable and transportable with no hassles is well worth it. Now, why else do I say that? There is a NSF DST program for research between India and the United States that funds it. And you may like to apply for that grant working with your friends in India, and you have great connections in India, Shiva. So the two of you may put it together to make it happen.
Yeah, I think there is in fact, it's nice that you mentioned this. One of my former students has set up a huge machine shop in India, His name is Arun Arunachalam. In fact, they're a very, very large manufacturer of multiple products for aerospace industry in India. And they do a lot of machining. They do enormous amount of machining. So he was talking to me about some of the things about how he connects with multiple people. He has put up his own little supply chain that he has connected himself with multiple small companies. So yeah, I think there is a lot of people in India. There are a lot of movers and shakers out there who are doing extremely well in India, who have, I mean, it's an up and coming economy. And I think, some of the pockets, in fact, they're setting up in Nagpur, they're setting up a full aerospace consortium of small manufacturers, big manufacturers connections. And there are multiple places like that. So yeah, India is doing a lot of good things. I mean, like we would certainly have a market if Harsh chose us to go back. There will be certainly a market there.
Great. If there are no further questions, Harsh, anything to say?
Nothing. Thank you, Dr. Raman, for the presentations. I really enjoyed a lot because of if I'm thinking working in India as a design engineer, I worked with the different kind of valves where I designed few valves and I learned the software as well. So it was great presentation on the 3D design.
Thank you.
Great. So I'm going to stop recording, and in our usual way, we go into the chit